All right, so we're going to talk about chi-squared, and the idea behind chi-squared is primarily we want to be able to compare multiple runs of data, if you will, is a way to think about that. So kind of jumping into the explanation behind what I mean is, let's look at a data set here based on degrees, or degrees based upon gender as they're earned: associates, bachelor's, master's, professional, doctorate degrees. Professional degrees might be classification like a specialist, PhDs, EDDs, MDs, DSSs, things like that. So those would be professional degrees that go beyond a master's, or maybe in some cases run parallel and different than a master's. And these are the counts based upon male and female counts. I'm strictly sticking with male and female. We can have all sorts of other discussions, but this is a simple discussion at this moment in time, and that's what we're going to stick with. So what we did here is we actually have the totals for the rows, and we have the totals for the columns across the bottom there, and then we have the total. And these are the degrees as awarded, okay, or earned. It maybe is a better way to say that. And the question that we're asking, and we're going to go ahead and jump over, and how do we compare this? So, like, is there what can we draw out of this? And the question we're asking here is are they the same? So our null hypothesis is there is no difference of degrees based on gender, and the alternative is that there is a difference of degrees earned based on gender. So, popping back to here, we look at this table again, and we're like, well, how can we tell? What's the process that we need in order to be able to determine whether there is? This is essentially what we call a two-way table, which means we're looking at multiple values in different directions. And these values allow us to be able to compare and contrast the difference between these things. So looking at associate's degrees, we see 396 versus 615. So roughly twice as many women, maybe not quite twice as many women got associate's degree as men. Look at bachelor's, and we see that there is still a discrepancy. We're talking about 800,000 versus 1.1 million. Master's, we got 250 versus 444. And then over here in professional, we have 71 versus 92. So is there a difference based on each individual degree based on gender? Okay, the degrees earned. So how do we do this? Well, the first thing we need to do is we need to talk a little bit about, once we have our hypothesis test set up here of what we're actually going to be looking at, is we need to make a couple of discussions first. And this is the process we're going to go through. We want to find the expected values based on percentages. That's what we're going to look at, the proportions between these things of the populations. And it's important that we remember that we're looking at populations here and not the samples. Yes, we're going to be using the samples, but the discussion is about the population. And a quick discussion about that is when we talk about a parameter, we're talking about the overarching idea that we're dealing with the population. The statistic is the individual sample piece. So we're going to use samples to discuss about populations. That's one of the big concepts that we're going after here. So what we have here is we're going to use this formula: observed value minus expected value squared, and then divide by the expected value. And we're going to add all those together. That may not make sense, but I'm going to jump over to a spreadsheet here, and it'll help a little bit. Degrees of freedom, we do have an idea of degrees of freedom here, and a short discussion on degrees of freedom is simply meaning how much space can we take up, if you will, about or around the things that we can do with the data. How many assumptions are we making, if you will, is another way to look at that. And in this particular instance, we have the number of rows minus 1 times the number of columns minus 1, so we can jump back over to the spreadsheet and see very quickly. We have 2 rows minus 1, so that's 1, and we have 4 columns minus 1, which is 3, so 3 times 1 would be 3. So our degrees of freedom here is going to be 3, okay? And then we use the chi-squared table once we get that value, or we use the TI-84 feature or some other feature like that. We can also do this with Minitab and SAS and R and Python. All sorts of other things will give us these values. But anyway, we're going to jump over for a second to the spreadsheet. At least I think we will. Oops. Let's see here. There we go. There's the spreadsheet. Now, what I did in the spreadsheet here is I actually found the row 3 and row 5 here, and these are the expected values based upon percentages. So what I'll do here is I'll click on this value right here. That, of course, is the sum, right, for that row. And I'll exit out of there, and of course, this value down here is the sum. Notice what it's the sum of, though. It's not the sum of the entire row. It's just the sum of those two individual cells, which are the counts that we had, right? Okay, those are the observed counts. Now, when I click on the expected value here, this expected value, the way we found that, and there are different ways you can do this based upon percentages. You could also go through and find the percentage of each individual component. But a shortcut way of doing this is to take the total for that row times the total for the column and divide by the total. All right, meaning like if you add column F up, you get this number. If you add row 6 up, you get that same number. It's not those two columns and rows added together. It's one or the other, and they should match. So we do that, and then we do the same thing for each expected value here. So there I did the total for the row times the total for the column divided by the total. And total is more of a me term than a actual professional term, but it's a functional term, so that's why I'm using it. And I do that for each individual value there. Once again, it's the row times the column divided by the total, okay? And I did that for all the way across. Now, the formula for chi-squared, what we did there is the expected, I know this is a lot to look at, but what I did there is B2 minus B3, so this is B2 minus B3 right there. So I subtracted the count minus the expected, and I squared that, and I divided by the expected, and I did that for each individual one. So for bachelors, for males, I did the count minus the expected, I squared it, and I divided by the expected, and that gave me B4. That was C2 minus C3 over there. So I did right here B4. B4 is right there. That is, for females, that is the count minus the expected squared and then divided by the expected value there. And we did that all the way across. Now, when we did that, we ended up with this number here, which is quite large. So this is, Excel doesn't do this really pretty, but I need you to assume that this is chi-squared, not x-squared. Okay, so my chi-squared value here, my test statistics, is 8860.92133. Okay, so when I do all of those calculations based upon this formula right here, observed value minus expected value squared divided by expected value, and this little sigma, this is sigma right here, this E-looking thing, that means add all these things together. So do it for each individual piece, each individual row column combination. You do all those together. And when you do that, you get some value. That's your chi-squared statistical value. We have our degrees of freedom, which are 3. I'll come back to that bottom line there and explain the calculator procedure there. Here, we look at degrees of freedom. There's 3. And then we find 8896, whatever that value was, right? So if you remember, what we had was when we looked at the spreadsheet, we had this value here of 8860. I'm sorry, 8860. When we look at the chi-squared table here, we have going across here, it doesn't actually go up. So this value right here is what we're looking for. It doesn't go up to 8860. It only goes to 16, but look at the value right here. This is our p-value, right? So that's the value that we're essentially dealing with at this juncture is what significance level this is. So we can actually go either direction with this. So we could say, if we wanted to be able to determine or make a test here, we could say, well, this significance level is pretty close. This is essentially 999 at this point, or 99.9% confidence interval. So what I'm doing here is, or the statement I can make is at this point is that this 8860 value with a corresponding degrees of freedom of 3 means that we have a p-value of 0.001. It's actually less than 0.001. Now, another way we could do this, and this is a little bit more of an interesting way to look at this, or maybe more useful, is if we go back to the calculator and we use this process, which is ChiSquared. You can find this on your calculator on the 84. I don't know the keystrokes for others, but all of them have it. All graphing calculators, scientific calculators, a lot of scientific calculators will have this as well, but all graphing calculators will have this functionality. On the 84, if you go to stat, oh, I forget. I think it's stat and then test. No, I'm sorry. You go to second vars, which is distributions, and you can go to option 8, which is ChiSquared CDF, and that will actually pull that up for you. It asks for your lower bound, your upper bound, and your degrees of freedom. So what I did was in the calculator, I typed in 0, 8860.9. You can keep going further, but that's not going to really matter with such a large number anyway. If this was a smaller number, like if this was 16, we'd go 16.9, and we'd probably go 2 or 3 decimal places out for accuracy. And then 3 for my degrees of freedom. So I'm going from 0 to 8860. And that's going to give us a value on the calculator. When we do that, it actually gives us a value of 1. Because the calculator, this value is so huge that you're actually talking about the number of zeros between the decimal point and the actual value that we get to. The first non-zero value is such a large value, the calculator just turns it into 1 at that point. So then we do 1 minus 1 to get the value. So we take whatever value the calculator gives us, which in this case is 1. We do 1 minus 1, and that gives us a p-value. So here the p-value actually ends up being 0. So what does that mean? Well, if we go back to our hypothesis test here, what it means is that we would reject the null, meaning that there is a difference. So we would come back and we would have had a p-value of 0, which is less than 0.05, which is our significance level. And that p-value of 0.00, however many zeros we want to go out, one way is it's less than 0.001, right? Means that we reject the null, which tells us that there is a difference in the degrees earned based on gender, which some of you say, well, that's obvious, look at this. But remember, a lot of times what we do in statistics is we're actually answering that question of, can we quantify what we're actually measuring? And that seems like a weird way to say that. We measurements are, by their sheer nature, are quantifying, right? So here we're saying, is there a true difference between 396 and 615 in terms of those being hundreds of thousands, right? So yeah, there is a difference between those two things. There is what is the difference? Which one's larger? Which one's smaller? Well, we can look at the data set and we can say, oh well, females are earning more degrees, right? But what we can say now with definity is maybe not with definity is the right word, but what we can say is that there is evidence to support. There's data to support. The evidence supports that there is a difference between degrees earned based on gender. We can make that statement now instead of just saying, well, it looks like there could be. Now we can say the evidence supports that, and that's what this test allowed us to be able to do. Okay, and that's the basis for that. There are other ChiSquared processes you can go through as well. This is one of them. There are other things you can do, and I encourage you to go look some of those things up as well. And if you need additional videos on this, please reach out and let me know, and I will do my best to get those posted. Take care.